BYD claims near magic efficiency with their integrated power electronics. But is it real-world savings or marketing spark? Let's tear the cover off the numbers. Today we dig into the ATTO 8's power electronics story, the 8-in-1 integration BYD talks about, the efficiency percentages they advertise, and whether early independent data backs that up. I'll show the exact figures BYD uses, explain why integration can cut losses, and compare lab claims to what real drivers and testers are seeing on the road. By the end, you'll know whether BYD's efficiency is a real advantage and what to watch for if you're buying or testing one. Hello everyone, I'm Shayan, an engineer specialized in electric vehicle development. What BYD says, the headline numbers. BYD has promoted its 8-in-1 electric powertrain and e-platform story across multiple models. On BYD marketing pages and product material, they point to high efficiency and publish an overall system efficiency number that they state is up to about 89% for the integrated electric powertrain. A figure tied to the benefits of packing motor, controller, DC-DC converter, onboard charger, and other into a tightly integrated unit. Those materials also claim reduced power consumption per distance versus older platforms. That 89% system figure is a headline. It bundles multiple parts of the electric chain, motor, inverter, transmission, DC-DC converter, and etc., to show overall drivetrain efficiency. BYD's pitch is vertical integration. When you control chips, motors, and software in-house, you can shave inefficiencies out of interfaces and wiring that other OEMs must solve across suppliers. Yole System Plus and other analysts have documented BYD's push towards system integration, the so-called 8-in-1, arguing it brings compactness, weight savings, and BOM cost reduction, and can raise real system efficiency if done right. Why integration can legitimately help efficiency? Let's make the engineering simple. Every electrical interface, every connector, every extra length of wiring is another place current meets resistance, makes heat, and loses a bit of energy. Integrating subsystems into fewer modules reduces the number of connectors and length of the interconnects. So you reduce the heating losses and eliminate some convergence steps. That's not marketing, it's basic physics. In addition, BYD designs and manufactures its own semiconductors and IGBT or silicon carbide modules. Public analysis of BYD's semiconductor work shows their integrated IGBT modules can achieve very high efficiency in specific hybrid modules. Analysis has claimed inverter or IGBT efficiencies up toward the high 90s in targeted use cases. Some quoted figures in industry commentary include module efficiencies like 98.5% for particular high-power units. Vertical control over the semiconductor and inverter stacks let the BYD optimize switching strategies, cooling, and packaging in ways many OEMs can't if they buy everything from different suppliers. That can meaningfully reduce inverter losses in real cars. The practical meaning of an 89% system. An 89% drivetrain number is useful but needs unpacking. That percentage typically represents the fraction of battery energy that makes it to the wheels under a practical test condition. It folds together motor copper iron losses, inverter switching and conduction losses, gearbox friction, and even DC-DC conversion losses. A high number means less energy wasted in the drivetrain. That can extend range or reduce consumption at the same speed. But it's not a single constant. Efficiency varies strongly with speed, torque, temperature, state of charge, and things like this. Figures may come from narrow operating points chosen to look best. Real driving cycles show more variance. Academic reviews and recent RxSieve analysis emphasize the importance of duty cycle when comparing efficiency claims. Where claims and reality often part ways. The hard part, marketing numbers are usually peak or optimal condition figures. Independent range and energy use testing has repeatedly shown EVs often use more kilowatt-hour per kilometer in real drive than lab WLTP numbers. And BYD models have seen this scrutiny too. Australian independent tests and reporting have flagged that some BYD models use notably more energy in the real world than their lab ratings suggested. A reminder that system efficiency on paper doesn't automatically translate into lower on-road consumption for every user or every route. That gap is the central challenge when assessing BYD's power electronic claims. Two key reasons the gap appears. Efficiency numbers can be measured at a single operating point, for example, a moderate speed on a dyno, that maximizes drivetrain efficiency, while daily driving includes stop, start, hills, cold start, and HVAC loads. That changes the picture. Integration reduces some losses but can concentrate heat. If thermal management isn't perfect, the system may throttle or operate less efficiently in real heat or cold, offsetting some gains. What independent data and early tests show? Independent testers and journalists have started to publish early real-world ATTO 8 and similarly equipped BYD models consumption numbers. The pattern seen in multiple markets is familiar. The cars often deliver very good efficiency in gentle, steady conditions, but real urban driving or highway runs with climate control pushes consumption higher than ideal numbers. Which car and other outlets have highlighted the general industry problem that claimed lab efficiencies don't always hold in the real world. And BYD models have been included in that scrutiny. That doesn't mean the 18-1 concept is false. It means context matters. Where integration gives measurable gains and where it doesn't. Wiring length and single thermal zone can cut parasitic losses and allow more compact cooling systems. Fewer power conversions, for instance integrating DC to DC conversion and onboard charger functions intelligently, reduces stepwise conversion losses. That's add up. The all systems analysis highlights how BYD's in-house approach yields weight and packaging benefits, and claims of 10% lighter assemblies and reduced BOM costs, all of which help system economy and therefore range. Integrated modules are complex to cool and repair. If the integrated inverter or motor runs hotter in sustained high power, efficiency and longevity can suffer. Also, integration reduces modularity. A single failed integrated module may be a costlier repair than swapping a single supplier component. That's more of an ownership risk than an efficiency one, but it factors into total cost of ownership. Sophisticated cooling and wide bandgap semiconductors like silicon carbide can offset that heat problem but increase upfront cost. Industry analysis note this cost or benefit balancing act as manufacturers push 8-in-1 architectures. Industry analysis note this cost balancing act as manufacturers push 8-in-1 architectures. If a traditional multi-box drivetrain has, say, 85% system efficiency at a useful operating point, the BYD's integrated approach raises that to 89% in the same condition. The difference is meaningful. A 4% point improvement on drivetrain efficiency means roughly 4% more energy to the wheels for the same battery output, directly translating into a similar uplift in range at the operating point. But remember, this is conditional. If that improvement disappears when HVAC is running or in cold weather, the net gain over a year can be smaller. The takeaway, high single-point efficiency is valuable, but the integrated system must maintain that edge broadly across real driving conditions to deliver clear buyer value. The test you should demand. If you're evaluating the ATTO 8's or similar cars, the real question isn't the peak efficiency BYD reports. It's how the integrated powertrain performs over a realistic mix: city traffic, highway cruising, cold mornings, hot afternoons, and with HVAC running. Independent long-term energy use studies and fleet trials are the only way to validate whether the 8-in-1 delivers consistent gains. Early signs are promising. BYD's vertical integration gives its tools, others don't. But independent testers show that WLTP or lab best case numbers remain optimistic compared to average user data. In short, BYD's approach can be a masterclass in efficiency if the integration holds up across real-world conditions and thermal cycles. Otherwise, the gains may be narrower than the headline suggests. BYD's ATTO 8 and the broader 8-in-1 strategy are real engineering choices that can and do reduce losses. BYD's vertical stack, including its own semiconductor and integrated modules, gives it an edge to optimize inverter switching, reduce interconnect losses, and shrink packaging. That's where the efficiency claims come from and why the overall system figures like 89% is plausible as peak or optimal point. But don't accept headline percentages without context. Look for independent mixed condition testing that measures the car in the situations we drive in: cold starts, city runs, highway trips, and with air conditioning on. If real-world tests show a consistent advantage across those conditions, the integration is delivering real value. If the advantage shrinks to a marginal few percent, only in ideal cases, the practical benefit for daily drivers will be smaller. Recent independent testing across the industry shows that lab-to-road gaps exist, and BYD has been included in the scrutiny. A healthy reminder to demand real numbers. If you want to learn more about the battery management system inside electric vehicles, how do they perform the safety checks? How do they calculate state of charge, state of health, and you want to analyze the battery management system, then click on the BMS course in the bio or in the description. The link is below. Thank you.